This lecture entitled Can't the Machines Do It is going to relate heat to work that we've learned about a little bit before using the laws of thermodynamics. So it says the Industrial Revolution was another one of those extraordinary jumps forward in the story of civilization. And the Industrial Revolution was where we first started to harness this idea that heat can be converted to work and actually other forms of energy as well, like electricity. And hopefully we never get to this particular point right here where we have machines that come back at us. So your learning goals for this particular lecture are that you understand the relationship between heat and mechanical energy. Okay, it's another step in the law of conservation of energy. You should be able to understand the laws of thermodynamics on both a macro and microscopic scale. And as an extension, for those of you who are moving just a little past the TEEKs, is that you should be able to calculate an unknown variable using the first law of thermodynamics. So, we start with what we already knew. We already knew that heat could be added with no change in temperature. And we said in this particular case, when you have heat that's being added with no change in temperature, we said that it's usually changing the phase. In this particular case, it would be probably vaporizing or changing from a liquid to a gas, and here it would be, melting. But there's also another place that you can actually take energy and go to. And so in the lab, what we did is we said we heated the liquid, and the liquid can actually cause a phase change. We talked about that. But in the lab, we actually developed an apparatus that used the energy of the heat. So whenever we had this vapor that kind of escaped, that vapor had energy, and the energy, the kinetic energy of the gas, was actually used to turn a pinwheel. Whenever you use it to turn a pinwheel, then you've actually done work. You've used heat to generate work. And so the gas was actually used to do physical work on the system. So, in other words, we're now relating heat to work, which is the main type of energy that we talked about when we talked about energy. Because remember, work can be related to any other energy. Work can cause kinetic energy, work can cause gravitational potential energy, work can cause elastic energy. So, by relating heat to work, you can now relate heat to just about any other energy. So, this unit is pretty intensive in terms of its vocabulary. So we're going to start off with just a couple of key terms. Number one being the system. The system is the collection of matter that's being studied. Generally, it indicates a sample either in a beaker or a sample of water in a reservoir or something that you're heating or some system of sometimes it's a gas molecules that you're heating or compressing or something along those lines. But the key thing is the system is what you define it to be. Now you generally the system is defined for you in a question, but you need to be very careful to separate the systems from the surroundings. Now the surroundings is everything else. So for example, if the systems is water in a beaker, then the surroundings would include the beaker, the air around the beaker, the room that the beaker is in, the universe, everything else is the surroundings. Thermodynamics is really what we're studying in this particular video, and that's the study of how heat and work are related. And another key term that you need to understand is the idea of entropy. And entropy a lot of times is defined as the disorder in a system, and that's kind of a misnomer definition. Really, entropy what it is it's energy without the ability to do work. What it generally represents is, well, we'll get into it a little bit later, but generally what it represents to is you can no longer capture the energy and use it to do work like we did in our experiment. Now, entropy is going to be a key concept, so you need to make sure that you pay attention to that when that comes up. But first, what we want to talk about is the zeroth law of thermodynamics. And the zeroth law of thermodynamics is if two systems are in thermal equilibrium with each other, then they are in thermal equilibrium with one another. So for example, if these two systems are in thermal equilibrium, remember there's no exchange of heat. So generally speaking, that means they are the same temperature. Well, if this one is in thermal equilibrium with the 50, and this one is in thermal equilibrium with the unknown, all of these things have to have the same temperature. Now that's just common sense, and that's why it's the zeroth law. It's kind of something that's understood that you should know beforehand. If these two are the same temperature and these two are the same temperature, then all three of them have to be the same temperature. Well, the zeroth law of thermodynamics is not really important. A lot of times it gets left out because it's just kind of understood. But really, the first law of thermodynamics is really where we need to start. The first law of thermodynamics says that heat and work are forms of energy. Okay, once we define them as energy, we know that energy cannot be created or destroyed, but instead it can flow into and out of a system. Okay, That should sound very familiar. It sounds just like energy cannot be created or destroyed, only converted from one form to another. And that should sound very, very familiar because that is our law of conservation of energy that we talked about in such detail in the previous unit. Okay, because of that, the first law of thermodynamics is just a restatement of the law of conservation of energy to include heat. Okay, now heat can be used to convert into mechanical energy like you see here. This is crucial to your way of life. Okay, heat being converted to mechanical energy is the source of almost all electricity that is generated. Okay, all electricity goes through this process. Okay, you have nuclear power, coal, oil, natural gas. What those all do is they provide a source of heat that is generally used to heat water. Whenever you heat that water up, it is able to convert into steam. And that steam, when it heats up, is allowed to turn a turbine, just like you did in the experiment. That heated water turns the turbine, and generally, that turbine is kind of a series of magnets that allows you to generate electricity. But basically, what you're doing is you're heating the water into steam, and then the steam has kinetic energy and therefore can do work on the turbine. Whenever it does work on the turbine, electricity is produced. And actually, this step right here is something that we'll cover later in the year, and it's called electromagnetism. Okay, so you really need to be able to take a look at these and say, follow the flow of energy, and it all starts with this idea of heat. Likewise, the opposite is also useful. Whenever you take mechanical energy, you can actually generate heat. And you see this more often as an incidental. You don't really generally want to generate too much heat. You can whenever you have an electric heater, but usually speaking, you want to do to avoid this particular process. And an example of this is if you have a rail car moving like a railroad car, and all of a sudden that railroad car has to slam on the brakes. Okay, a lot of times when they slam on the brakes, you see sparks flying, and there's all kinds of you tend to see it in movies, but it is real that you have sparks that start to fly because whenever you have this mechanical energy and you come to a stop, whenever you come to a stop, that energy has to go somewhere, and generally it goes into work, which is then produced into heat by friction. So this is not a particularly useful, I mean, it is sometimes, but generally speaking, we would rather go from heat to mechanical energy instead of mechanical energy to heat. So all of the energy goes into raising the temperature. So here's an example, and this is using the idea of the first law of thermodynamics. This is the piston in an engine is capable of expanding a distance of 0.1 meters. Okay, it says the expansion occurs such that there is no net change in energy of the system. So basically it's saying that the amount of energy has to remain the same. How much force does this piston expand with if the expansion occurs as 500 joules of heat is added to the system? So what I'm saying is I'm taking 500 joules and I'm putting it into the system. But what I'm saying is the system has no change in energy. So what that means is I have to take 500 joules out of the system. Okay? And the only way that I can take that work out of the system is if the system does work by expanding. Okay? So what I'm saying is that the system expands with 500 joules of energy as a result of there being no change in work. So what I can say is that the work is equal to 500 joules. Okay? It says that it expands a displacement of 0.10 meters. And what you're trying to solve for is you're trying to solve for the force. So really what this question boils down to is one of the earlier examples that we did in energy, which is just work equals force times distance. W equals FD. When you do this, you would say 500 equals F times 0.1, divide both sides by 0.1, and what you'd end up with is you'd end up with a force of about 5,000 newtons, which is a pretty strong force for a piston to expand with. Next, what we do is we take a look at the next one. It says a fire syringe, and you guys may have seen a fire syringe when you did this in chemistry, okay? But a fire syringe, it creates a spark as gas is compressed. It says there is no net change in energy of the system. It says you have a 5,000 Newton force that is necessary to compress the cylinder by 0.2 meters. It says The cylinder contains 2 grams of air. It gives you a specific heat, initially at 23°C, and it says what is the final temperature of the air as it's being compressed. So we're once again saying that there is no net change in energy of the system. So what I'm doing is I'm pressing down here, and when I'm pressing down there, I'm putting work into the system. But by saying there's no net change in energy, what I need to say is all this work is then converted into heat. So now what I want to say is, now that I know that it's converted into heat, I can say, okay, 0 equals Q plus W, because there is no net change in energy for the system. So in other words, the work that I do putting it into the system is equal to the heat that is gained by the system. So that's what we can say. So now I can look and I can calculate my work. Remember that work is equal to force times the displacement, and Q is equal to Cm delta T. So we plug all this stuff in and we say, okay, 5,000 times 0.2 equals the specific heat of air was provided to us. The mass of air was provided to us. And then also, we want to know what the final temperature is. So we can say TF minus 23. And a lot of you may be concerned at this point because you say, well, wait a second, you had 2 grams of air. What happened there? Remember that you had 2 grams of air, but you also had your specific heat capacity was in joules per gram. Remember, those two things cancel out in this particular case. If you want, you can convert both of them, but they're going to cancel out anyway. So once you do this, you would expand this out, and you would solve for the change in temperature. The change in temperature ends up being about 498 degrees Celsius. So since that is the change in temperature, we can actually leave this as delta T. When you solve for the change in temperature, now you can go ahead and say, well, if there's the change in temperature was 498 degrees, then what you can do is you can say, okay, well, if the change in temperature is 498 degrees, you add 23 degrees Celsius to that, and you would get your final temperature. Now, if you're not comfortable with going from the math here to this particular number, you need to go ahead and check with your teacher, because you should be able to multiply these two things, and you should be able to multiply these two things, and you should be able to divide in order to get that 498 number. The next example says, a balloon is filled with a gas and sealed off from the rest of the environment. What is the change in energy of the system when 500 joules of heat is added, resulting in 200 joules of expansion? So basically what we have here is something a little bit different. We're saying that we put 500 joules of energy into the system, but instead of getting 500 joules out like we have been doing in the last two examples, it says that only 200 joules of energy come out of the system. So this is saying, what is the change in energy for the system? Well, if you put 500 joules of energy in and 200 joules of energy comes out, what the net of that is would be 300 joules of energy that goes into the system, because 500 joules out, 500 joules in, 200 joules out means that you have 300 joules of energy that's still in the system that wasn't there before. A lot of times people will express this as delta U, which stands for the change in the internal energy of the system, but you can also write it just as delta E, or just 300 joules in this particular case. Next, we need to talk about heat engines. A heat engine is any device that converts between heat and work, and there's a lot of them that do that. Things like engines take heat and use it to create work, and then therefore kinetic energy for your car. Refrigerators are things that actually do work on the gas in the refrigerator in order to take the heat out. And a refrigerator is basically the same thing as an air conditioner. And then even a bimetallic strip, whenever it's heated, okay, if you know what a bimetallic strip is, it's a strip of metal that consists of, or it's a strip that consists of two different metals, so metal A and metal B. And whenever you heat this bimetallic strip up, well, it does work in curling the strip up, so it actually curls it into a ball. So anytime you heat something up and it moves, what you're doing is that's a heat engine. Now, some heat engines are more interesting than others, especially things like engines and refrigerators. But anything that heats and moves as a result of that would be consistent with a heat engine. So if you were to take a stopper and put it on a flask and then heat up the water in there and it pops the flask off, technically that's a heat engine because you've converted between heat and work. One of the most common examples, or not common examples, but one of the best examples of a heat engine is geothermal energy. Now, a lot of people have talked about geothermal energy as a way to reduce our heating and cooling costs in our house and actually be able to create electricity as well. Is the fact that the earth is always a constant temperature, and so you can actually heat water using the earth and use that steam to turn a turbine and therefore produce electricity. Okay, then you kind of see that right here. You have an injection well where you pump water down into the earth. That water heats up and it reaches a flash tank. And that flash tank, then you have steam that's used to turn a turbine. And then after it turns the turbine, it condenses and comes back through where it's injected back into the ground again. So the point of this is you're not actually using as much energy as you normally would because you're actually raising the temperature of the water by using the heat of the earth itself. So the steam turns a turbine and produces electricity, and it's kind of a cycle. So you're actually continually using the same water and creating electricity that way. So a geothermal plant is very useful, and that leads us into our second law of thermodynamics. And the second law of thermodynamics says that the heat spontaneously flows from high temperature to low temperature, and we already knew that. We said that that was how you reach thermal equilibrium. You have something that is a high temperature, you have something that is a low temperature, and the heat will always flow in this direction. It never spontaneously flows in the other direction. You can get it to go in the other direction, but you have to input some other sort of energy in order to make that work. And here's the key thing with the second law of thermodynamics: reactions are never 100% efficient. Okay, not just now, not just saying, hey, we don't have very efficient car engines and we need to work on that. Any sort of reaction that you have will never produce a 100% efficiency from one type of energy to the other. Okay, that leads us to kind of a discussion about entropy. Entropy is why you can't have 100% efficiency. The entropy of the universe always increases as energy is transferred. So if you think about it, if you're using the molecules of a gas to turn a turbine, when this molecule collides with the turbine, some of it is going to be cause the turbine to move. Some of it's just going to be absorbed by the turbine, and some of it may be scattered somewhere else. There are things that you can do to reduce this and make engines more efficient, but no matter what you do, the entropy of the universe is always going to increase. So, as temperature increases, entropy increases. As the phase change moves towards the gas phase, entropy also increases. And a lot of people have, examples of saying, well, but what about this? And it gets cooler. We're talking about the entropy of the universe overall, and we'll explore those in a couple of these examples. And the first one says the air conditioning breaks down on a hot day, so a student seals off the kitchen and opens the door to the refrigerator. Describe the temperature of the room and the temperature and entropy in the room. And so this is kind of a misconception that people have. They say, oh, if the refrigerator or if the air conditioning breaks, you can just open the refrigerator. And it doesn't work that way. On the back of the refrigerator is a motor, and that motor is actually used to pump the heat out of the back of the refrigerator and kind of put it into the kitchen. Now, generally, you don't notice it because the volume of air in the kitchen is much larger than the volume of air in the refrigerator. So you can actually decrease the temperature of the refrigerator without a noticeable increase in the temperature of the kitchen. But if the air conditioning breaks down and you leave the door open, yes, you are starting to cool this particular air, but you create more heat than you do taking the heat away because the reactions are never 100% efficient. So although you do cool a little bit of the air, you heat more of the air than you actually cool. So the net effect of this would be you would have an increase in temperature even though the refrigerator door is open. It may feel cooler if you're standing right by the door, but overall the temperature is going to rise. This one says which of the phase changes will increase the energy of, or excuse me, this should say the entropy of water. Which of these will increase the entropy of water? And the ones that will increase the entropy of water would be any one where you're moving towards the gas phase. So the first one would be, the obvious one is evaporation. Okay, evaporation is moving towards the gas phase because you actually get to the gas phase. So evaporation will increase the entropy of the water. And the other one would be melting. Okay, whenever you're melting ice into water, that actually moves you closer towards the gas phase. So you have melting and you have evaporation. Okay, those are the two phases that will increase the entropy. And people say, well, okay, how is the universe increasing in entropy whenever you condense or whenever you have rain? And the answer is it's not for that particular system, but overall for the universe. As an extension, we want to take another look at the first law of thermodynamics and some key vocabulary terms. What you see here is a bomb calorimeter, which is really useful whenever you're examining heat transfers. There are different settings that you can do on a calorimeter, but really what you're looking at is the first thing is an adiabatic situation, and we tried to approximate an adiabatic situation as much as we could in our solar radiation lab, but really that's really hard to do. An adiabatic one is a reaction that occurs with no change in heat. There's no heat that's transferred from one system to another, from the system to the surroundings or between two systems. That's really hard to accomplish, but what you can do is you can approximate it using styrofoam and having insulators and those sorts of things. An isothermal situation is one in which you maintain a constant temperature. Now, a constant temperature does not mean that there's not heat flowing from one to the other. It just means that the overall temperature, which means the average velocity of the particles in the system, remains constant. There are also situations in which you have an isochoric system. An isochoric system is one in which the volume is constant throughout, and that tends to be what you when you have a bomb calorimeter. This particular system right here is a very hard metal cylinder, and that metal cylinder cannot expand and it cannot compress the gas. So whenever you have that, the volume is restricted to that particular space. And then finally, you have an isobaric system, and that is where you have constant pressure. So, so if we take a look at the first law of thermodynamics again, they can actually be stated in equation form, which is delta U equals Q plus W, where delta U actually stands for the change in internal energy. Okay, so the change in internal energy represents how much energy the system is gaining or losing, depending on the situation, and it is measured in joules. So that's the only thing that's really new, and we talked about it real briefly in one of the examples, but delta U is the change in internal energy. You also have Q plus W. Now, it's really important that when you have these particular systems that you need to take a look at them and you need to be able to define Q and W as being positive or negative. For our purposes, and it varies from book to book, we're going to say that Q is positive whenever heat is transferred into the system. So whenever you have a system of molecules, let's say it's a beaker of water, whenever heat flows into the system, we're going to call that positive. And whenever heat flows out of the system, we're going to say that the heat is negative. Okay, and that's pretty easy to remember. The one that's a little bit more difficult and the one that varies from textbook to textbook tends to be the work. And we're going to define work as being positive when it is done on the system. Okay, whenever you're taking and you're squeezing the container, maybe it's a balloon filled with gas. Whenever you're squeezing the container, we're going to say that you are doing positive work on the system. And that's because you're actually adding to the energy of the system, because as you compress the system in, it's in a higher energy state. It doesn't want to be there. Okay, so we're going to say that that's the positive W value. Then we're going to say that work is negative in the opposite situation whenever it's expanding. Whenever work expands outward, or whenever a system expands outward, it's actually becoming more stable, so it's losing energy. So we're going to say it's negative in that particular case. It's really important for these particular equations that you get that straight. You also need to take a look at pressure. It says pressure. Humans can actually detect pressure much easier than force, and you can actually experiment with this if you put your hand on a flat surface and put your other hand on it and press down. It usually doesn't hurt very much, but if you use the same amount of force using something like a pencil tip, don't do that obviously, but you can actually feel the pressure much easier. So pressure is the ratio of force to area. And you can see that right here. It's F divided by A, and it's used as the units are pascals is the standard unit. Although if you're familiar with from chemistry, you talked about kilopascals and you talked about atmospheres and you talked about millimeters of mercury. There's lots of different ways. You can actually measure it directly with a pressure sensor. Not really directly, but it works for our purposes. Everything else is the same. So you have force, which we've talked about, and then you have area, which is A. And those are both measured with meter sticks and Newton spring scales. So you can actually take Newton's first law, or excuse me, not Newton's first law, the first law of thermodynamics, and you can actually expand it outward. So delta U equals Q plus W can be expanded into P delta V. So you can actually take these things and you can use this equation for very specific circumstances. So for example, whenever you have an adiabatic situation, that means there's no heat transferred. This particular term crosses out, and you would say that delta U equals P delta V. Okay? Or for an isothermal situation, whenever you have a constant temperature, what you would say is that there's no change in internal energy, and Q plus P delta V has to equal 0. Whenever you have an isochoric system is one that has a constant volume. Now remember, work was equal to force times distance, and the object had to move. Well, the same situation occurs right here. It's P delta V. Okay, in order for an isochoric system to have work done on it, it actually has to move. So whenever you have a constant volume, the change in volume is 0, and 0 times whatever the pressure is going to cancel out. And so for an isochoric system, you'd have delta U equals Q. It just equals Q. Okay, and the last one says constant pressure, and constant pressure actually has no change on the particular system because you're just keeping this number the same. It's not a delta term. So because of that, an isobaric system, the equation is as it is. So let's apply these to a couple of different equations, and we have example C1. Example C1 says that the adiabatic expansion of a gas, so because I know it's adiabatic, I know that delta U has to equal P delta V. Okay, adiabatic means there's no change in heat. So it says the expansion of a gas decreases the internal energy of a system by 200 joules. What is the pressure of the gas during this expansion? So it's decreasing. Okay, so we have a negative term right here because delta U equals W, and so since it is expanding, you're actually losing work here. So this term is actually going to be delta U equals negative P delta V. Okay, so now we can plug in our terms and we can say it loses 200 joules, negative, trying to solve for P, and the change in volume in this particular case is 0.1. So if you notice right away, the negative signs cancel out. You divide both sides by 0.1, and when you do that, you end up getting about 2,000 pascals of pressure. Now, 2,000 pascals of pressure actually isn't that much. It's a lot less than the actual atmosphere, so that's a completely reasonable answer. The next one says you have a bomb calorimeter that's a useful device in examining the energy per kilogram of a material. It says the calorimeter burns the excess oxygen to produce a gas under isochoric conditions. What is the energy per gram if 0.319 grams of unknown sample is combusted, raising the temperature of 2 kilograms of surrounding water by 1.8 degrees Celsius? So, the key to this particular situation is it is an isochoric conditions. Remember, isochoric means that there is no change in volume. Because there is no change in volume, delta U is just equal to Q. So, if I'm looking for the energy per gram, okay, I know that the heat that is produced is equal to the energy of this particular sample. So, what I can say is Q equals Cm delta T. Now I'm going to do it just for the water in this case, okay, because the unknown sample is what I'm trying to find out about. So the heat that is produced is what's actually increasing the energy of this particular system. So you would say the specific heat of water is 4184, the mass of the water is 2 kilograms, and the change in temperature is 1.8 degrees. Okay, whenever you do that, you get a change in energy of, let's see, 4184 times 2 times 1.8, and you get about 1,000, it's about 15,062 joules of energy. But realize that the sample that you burned was only 0.319 grams. So because of that, you have to divide that by the mass of the sample, and when you do that, you get a very, very large number. of about 47,200. Hold on, having a hard time writing that. 47,200 joules per gram, which is quite a lot of energy when you're combusting it. Okay, the last example says in the 1960s, women were forbidden from wearing stiletto heels on airplanes due to the damage the heels inflicted on the floor. Determine the difference in pressure when a 75 kilogram woman wears stiletto heels with a surface area of 4.03 times 10 to the negative fifth or regular flats of 0.025 meters. So basically what we're doing is we're doing a pressure calculation for two different situations. Okay, so pressure is force divided by area. So we have the mass of the woman, and remember, the mass of the woman allows us to determine a force. In this particular case, it's going to be the force due to gravity divided by the area. Okay, the force due to gravity is not going to change for the two situations. It's going to be 75 times 9.8. And when we do 75 times 9.8, we're going to get a number of 735 newtons. So in one situation, we're going to have 735 newtons divided by 4.03 times 10 to the negative fifth. And in the other situation, we're going to have the same 735 divided by 0.025 meters squared. So when you divide those two things out, for the first situation with the stiletto heels, you're going to get 18,200,000 pascals of pressure, which is an enormous amount. And in the second situation, you're going to get 29,400 pascals, which is much, much, much less. So you can see why, when they were concerned about puncturing holes in an airplane, that they asked women to forego their stiletto heels when they were walking in an airplane.